For nearly half a century, Voyager 1 has been traveling through the cosmos, a tiny spacecraft that has crossed vast distances, leaving our solar system far behind. It's ventured further than any human-made object in history, yet it continues its journey into the unknown, uncovering mysteries that were once beyond our comprehension. But after 48 years in space, Voyager 1 is still asking the same question. What lies beyond the edge of the universe? Could it possibly reach the limits of our cosmic understanding? How far can it go, and what could it tell us about what's out there, beyond even the edge of the universe? As Voyager 1 moves deeper into the endless void, we may soon find out. Hello there, and welcome to the Slumbering Archive. I'm so glad you found your way here, and I hope tonight's journey will bring you peace and wonder. Whether you're settling in after a long day or drifting into sleep, let's take a moment to journey together through the cosmos to the edge of the universe with Voyager 1 as our guide. Before we begin this journey together, if you're finding comfort in these quiet words, a gentle like or subscribe would mean more to me than you might imagine. It's a small thing, but it keeps this little corner of the universe alive. Tonight, we explore the vastness of space, taking a long and peaceful journey with Voyager 1 to the very edge of the universe. There's nothing to do but relax and let your mind wander as we explore these cosmic mysteries. Picture this for a moment. On September 5, 1907, a rocket lifted off from Cape Canaveral in Florida, carrying a spacecraft no bigger than a small car. This was Voyager 1, and it was about to embark on a journey that would redefine our understanding of space itself. The scientists who designed it hoped it would last 5 years, maybe 10 if they were lucky. But here we are, nearly half a century later, and Voyager 1 still out there, still sending signals back to Earth from a distance so vast it's almost impossible to comprehend. Think about that for a moment. A machine built in the 1970s, with less computing power than the phone in your pocket, is still functioning in the harshest environment imaginable. It's traveled more than 15 billion miles from home, and it's still going, still exploring, still teaching us about the universe we live in. When Voyager 1 launched, its mission was relatively straightforward, at least on paper. It was designed to study Jupiter and Saturn, two gas giants that had captivated astronomers for centuries. Scientists wanted close-up images, detailed measurements, information about their moons and their magnetic fields. They wanted to understand these distant worlds in ways that telescopes alone could never reveal. And Voyager 1 delivered beyond anyone's wildest expectations. In 1979, it reached Jupiter, and the images it sent back were breathtaking. We saw the Great Red Spot up close for the first time, a storm larger than Earth itself, swirling with colors and patterns that seemed almost alive. We discovered new moons, including volcanic activity on Io, Jupiter's innermost large moon, something no one had predicted. Imagine that. Volcanoes erupting on a world hundreds of millions of miles away, captured by a spacecraft humanity had built. A year later, in 1980, Voyager 1 reached Saturn, the Io. Images of Saturn's rings were stunning, revealing a complexity that had never been seen before. The rings weren't just simple bands of ice and rock. They were intricate, with thousands of individual ringlets, gaps, and divisions, each one telling a story about gravitational forces and cosmic collisions that happened billions of years ago. Voyager 1 also discovered that Titan, Saturn's largest moon, had a thick atmosphere, something extremely rare for a moon. This discovery would later inspire missions dedicated entirely to studying Titan. But here's the remarkable thing. After completing its primary mission, After delivering everything scientists had hoped for and more, Voyager 1 didn't stop. It kept going. And in that continuation, in that journey beyond the planned destination, Voyager 1 began to reveal something far more profound than images of planets and moons. It began to show us the scale of the universe itself. As Voyager 1 moved past Saturn, it entered what scientists call the outer solar system. This is a region of space that's almost empty, a vast expanse where planets are few and far between. Out here, the sun is just another star, barely brighter than the others in the sky. The warmth and light that sustain life on Earth are distant memories. And yet, Voyager 1 pressed on, further into the darkness, further into the unknown. In 1990, Voyager 1 turned its camera back toward Earth one last time. From a distance of about 3.7 billion miles, it took a photograph that would become one of the most iconic images in human history. Earth appeared as a tiny pale blue dot, barely visible against the vastness of space, suspended in a beam of scattered sunlight. Carl Sagan, the astronomer and science communicator, described this image beautifully. He said that everything we've ever known, everyone we've ever loved, every war ever fought, every moment of human history, all of it happened on that tiny dot. Think about that for a moment. Let it really sink in. From Voyager 1's perspective, Earth was insignificant, a speck of dust in an ocean of darkness. And yet, for us, it's everything. It's home. It's where life exists, where consciousness emerged, where we've built civilizations and dreamed of exploring the stars. That photograph changed how many people think about our place in the universe. It reminded us of our fragility, our smallness, and yet also our incredible courage in reaching out to explore the cosmos. After taking that photograph, Voyager 1's cameras were turned off to conserve power. Its mission now was different. It was no longer about studying planets or moons. It was about studying space itself, the environment between the stars, the boundary where our sun's influence ends and interstellar space begins. And so Voyager 1 continued year after year, decade after decade. By the early 2000s, it had traveled further than any human-made object in history. It was in a region scientists call the heliosphere, a turbulent area where the solar wind, the stream of charged particles flowing out from the sun, begins to slow down as it collides with the interstellar medium, the material that exists between the stars. Instruments on Voyager 1 detected strange changes in this region. The solar wind was slowing down, just as predicted, but there were unexpected fluctuations, bursts of activity that scientists didn't fully understand. It was as if Voyager 1 was approaching a boundary, a threshold between two very different environments. And on August 25, 2012, Voyager 1 crossed that threshold. It left the heliosphere, the protective bubble of space dominated by our sun, and entered interstellar space. Think about that for a moment. Interstellar space, the space between the stars. Voyager 1 had become the first human-made object to leave the solar system's immediate influence and venture into the true emptiness of the galaxy. The data it sent back was fascinating. The density of particles in interstellar space was higher than in the heliosphere, and the magnetic field had changed direction. Voyager 1 was no longer in our sun's domain. It was in the domain of the galaxy itself, and still, it kept going. Even now as we speak, Voyager 1 is moving through interstellar space at about 38,000 miles per hour. That sounds incredibly fast, and it is by human standards. But in the scale of the galaxy, it's almost nothing. It would take Voyager 1 about 40,000 years to reach the nearest star system, Alpha Centauri, if it were headed in that direction. which it's not. The distances between stars are so vast that even our fastest spacecraft move like snails through the cosmic ocean. But here's where things get truly interesting. Voyager 1's journey, as remarkable as it is, raises profound questions about the universe itself. Questions about what lies at the edge of the universe, and more importantly, what might lie beyond that edge. To understand these questions, we need to think about what we mean when we talk about the edge of the universe. And that's not as simple as it might seem. Let's start with what we know. According to our best understanding of physics, the universe began about 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space. It was the beginning of space itself, the moment when matter and energy all came into existence. Everything that exists, every star, every galaxy, every atom in your body, all of it traces back to that singular moment. In the first fraction of a second after the Big Bang, the universe expanded incredibly rapidly in a process called inflation. Space itself stretched faster than the speed of light, carrying matter and energy along with it. This expansion didn't stop after that first moment. It's still happening today. The universe is still expanding, and as far as we can tell, that expansion is actually accelerating. Now here's where it gets tricky. When we talk about the edge of the universe, we're not talking about a physical boundary like the edge of a table or the shore of an ocean. We're talking about something called the observable universe. This is the region of space from which light has had time to reach us since the Big Bang. Because light travels at a finite speed, about 186,000 miles per second, there's a limit to how far we can see. Any light from regions of space beyond a certain distance simply hasn't had time to reach us yet. The observable universe has a radius of about 46.5 billion light-years. That's not a typo. Even though the universe is only 13.8 billion years old, the expansion of space means that objects we can see now are actually much farther away than 13.8 billion light-years. It's one of those mind-bending consequences of relativity and cosmic expansion. Light that left distant galaxies billions of years ago is just now reaching us, but those galaxies have been carried even farther away by the expansion of space in the meantime. So the edge of the observable universe is simply the distance beyond which we cannot see, not because there's nothing there, but because light from those regions hasn't reached us yet. It's a horizon, not a boundary. And like any horizon, it's relative to the observer. An alien civilization in a galaxy billions of light years away would have their own observable universe, with their own horizon, and it would be centered on them, not us. But here's the question that keeps astronomers and cosmologists awake at night. What lies beyond our observable universe? Is there more space out there? More galaxies, more stars, stretching on forever? Or is there some kind of actual boundary, some edge beyond which nothing exists? And if there is such an edge, what could possibly lie beyond it? These are questions that Voyager 1, for all its achievements, cannot answer directly. It's moving far too slowly, and it will never reach the edge of our solar system's neighborhood, let alone the edge of our galaxy or the observable universe. But Voyager 1 still plays a role in these questions, a subtle but important one. It reminds us of the scale of what we're dealing with. It shows us just how vast space is, even in our own tiny corner of the universe. Think about it this way. Voyager 1 has been traveling for nearly 50 years, and it's only just left our immediate solar neighborhood. It hasn't even reached the Oort cloud, a spherical shell of icy objects that surrounds our solar system at a distance of about 1 light year. That's how big our solar system actually is when you include all its outer regions. And our solar system is just one of hundreds of billions of star systems in our galaxy. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. The numbers are so large they lose all meaning. Our brains didn't evolve to comprehend distances measured in billions of light years. We're creatures of the savannah, built to understand distances we can walk in a day or see from a hilltop. The cosmos operates on a scale that's fundamentally alien to our everyday experience. And yet, here we are, trying to understand it, building machines like Voyager 1 to explore it, formulating theories about what might lie beyond the edge of everything we can see. Let's take a moment to consider what scientists think might lie beyond the observable universe. There are several theories, each more fascinating and strange than the last. None of them can be proven, at least not yet, because by definition, we cannot observe anything beyond our observable horizon. But they're based on mathematics, on the laws of physics as we understand them, and on logical extrapolation from what we can see. The first and perhaps simplest theory is that the universe just continues. Beyond our observable horizon, there's more space, more galaxies, more stars, all similar to what we see in our own cosmic neighborhood. In this view, the universe might be infinite, stretching on forever in all directions. There's no edge, no boundary, just endless space filled with matter and energy, all of it following the same physical laws that govern our observable region. This idea is both comforting and terrifying. Comforting because it means the universe is comprehensible, that what we see here applies everywhere. Terrifying because it means there's no center, no special place, no ultimate meaning to our position in the cosmos. We're just one planet orbiting one star in one galaxy in an infinite sea of similar structures. The universe doesn't care about us, it simply is. But there's a problem with an infinite universe, or at least a philosophical one. If space is truly infinite and matter is distributed more or less uniformly throughout it, then there should be an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if that's the case, then there should be an infinite number of planets exactly like Earth, with histories exactly like ours. There should be infinite copies of you reading these words right now in galaxies scattered throughout an infinite cosmos. Some copies would be slightly different, making different choices, living different lives. But others would be identical, down to the last atom. Think about that for a moment. An infinite universe means infinite possibilities, including infinite exact duplicates of everything we know. It's a strange thought, almost impossible to wrap your mind around. And yet, mathematically, if the universe is truly infinite, it seems to follow logically. Most scientists are uncomfortable with this conclusion, but they can't definitively rule it out either. The second theory is that the universe is finite but unbounded. This is a concept that's hard to visualize because it requires thinking in more than 3 dimensions. Imagine the surface of a sphere, like the surface of Earth. If you start walking in one direction and keep going, you'll eventually come back to where you started. The surface is finite, you can measure its total area, but it has no edge. There's no point where you fall off or reach a boundary. You can travel forever and never reach an end. Now imagine the same concept, but applied to 3-dimensional space instead of a 2-dimensional surface. The universe could curve back on itself in a way that makes it finite in total volume, but unbounded with no edges or boundaries. If you traveled far enough in one direction, you'd eventually return to where you started, though the journey would take trillions upon trillions of years, far longer than the current age of the universe. This idea appeals to many physicists because it avoids the problems of an infinite universe while still maintaining a kind of cosmic elegance. There's no edge to explain, no boundary where you have to answer the uncomfortable question of what lies beyond. The universe simply is what it is, a closed and self-contained system. Measurements of the cosmic microwave background, the afterglow of the Big Bang, suggest that if the universe is curved in this way, the curvature is very slight. The universe appears to be either flat or very nearly flat, which means it's either infinite or so large that any curvature is undetectable with current technology. The third theory ventures into even stranger territory. It suggests that our observable universe might be just one of many, perhaps even an infinite number of separate universes, each with its own physical laws, its own history, its own structure. This is the multiverse hypothesis, and it comes in several different flavors, each more mind-bending than the last. One version of the multiverse arises from the theory of eternal inflation. Remember how the universe expanded rapidly in the first fraction of a second after the Big Bang? Some physicists believe that this inflation didn't happen just once. Instead, it's a process that's always occurring somewhere in the broader cosmos. Our observable universe is a region where inflation stopped, allowing matter and energy to condense into galaxies and stars. But beyond our cosmic horizon, inflation is still happening, creating new pocket universes, new regions of space-time that are forever disconnected from us. In this scenario, the edge of our universe isn't really an edge at all. It's just the boundary of one bubble in an infinite foam of universes, each one expanding and evolving independently. Some of these universes might be similar to ours, with galaxies and stars and perhaps even life. Others might have different physical constants, different laws of physics, making them utterly alien and uninhabitable. And there's no way for us to ever visit them or observe them directly. They're forever beyond our reach, separated by regions of space that are still inflating faster than light. Another version of the multiverse comes from quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales. According to one interpretation, every time a quantum event occurs, an event with multiple possible outcomes, the universe splits into multiple versions, one for each possible outcome. This is the many worlds interpretation, and it suggests that there are countless parallel universes, each one slightly different, each one representing a different set of quantum choices. In some of these parallel universes, Voyager 1 never launched. In others, it crashed shortly after liftoff. In still others, it discovered something completely unexpected that changed the course of human history. Every possibility that could have happened did happen, just in different branches of the multiverse. It's a dizzying thought, and many physicists are skeptical of it, but it's a legitimate interpretation of the mathematics of quantum mechanics. And then there's the simulation hypothesis, an idea that's become increasingly popular in recent years, though it's more philosophy than physics. It suggests that our entire universe, everything we observe and experience, might be a simulation running on some unimaginably advanced computer. In this view, the edge of the universe would simply be the edge of the simulation, the point where the programmers decided to stop rendering space. Beyond that edge, there might be nothing at all, just empty code or perhaps other simulations, other universes running on the same cosmic computer. This idea sounds like science fiction, and in many ways it is. But some physicists take it seriously because it's surprisingly difficult to disprove. If we are living in a simulation, there might be subtle glitches or limitations that we could detect, clues that reality isn't quite as real as it appears. So far, we haven't found any such clues, but that doesn't mean they're not there. It's a humbling thought. The idea that everything we know, everything we've discovered, from atoms to galaxies to the journey of Voyager 1 itself, might be nothing more than an elaborate computer program. Let your mind rest with that for a moment. The edge of the universe, if it exists, might be something we can never truly understand, a boundary defined by limitations we can't overcome, either because of the physics of space-time or because of the nature of reality itself. But let's return to Voyager 1 for a moment, because despite all these grand theories and cosmic mysteries, this little spacecraft still has something to teach us. It's not going to reach the edge of the universe, of course. It's not even going to reach the edge of our galaxy. But what it's doing, what it will continue to do for as long as its instruments function, is measure the space between the stars. And those measurements matter more than you might think. You see, interstellar space isn't completely empty. It's filled with gas and dust, particles left over from ancient supernovae, the explosions of massive stars at the end of their lives. There are magnetic fields threading through the void, shaped by the rotation of the galaxy itself. There are cosmic rays, high-energy particles traveling at nearly the speed of light, originating from sources we don't fully understand. All of this makes up what astronomers call the interstellar medium, and it plays a crucial role in the evolution of galaxies. The interstellar medium is where new stars are born. When regions of gas and dust become dense enough, they collapse under their own gravity, heating up until nuclear fusion ignites in their cores, creating new stars. Those stars live for millions or billions of years, depending on their size. And when they die, they return material to the interstellar medium, enriched with heavier elements forged in their cores. This cycle of birth and death, of matter flowing from stars to space and back again, is what drives the evolution of galaxies over cosmic time. Voyager 1 is giving us direct measurements of the interstellar medium in our local neighborhood. It's measuring the density of particles, the strength of magnetic fields, the intensity of cosmic rays. These measurements help us understand not just our own galaxy, but galaxies throughout the universe. They help us refine our models of how stars form, how galaxies evolve, how the universe as a whole has changed over its 13.8 billion year history. And there is something poetic about that, don't you think? This tiny spacecraft built by humans decades ago is still contributing to our understanding of the cosmos, still sending back data that reveals new truths about the universe. It's a testament to human curiosity, to our desire to explore and understand the world around us, no matter how vast and incomprehensible it might seem. Voyager 1 is also carrying something else, something that has nothing to do with scientific instruments or data transmission. It's carrying a golden record, a phonograph disc plated with gold, containing sounds and images from Earth. There are greetings in 55 different languages, music from cultures around the world, sounds of nature like thunder and birdsong, and even the brainwaves of a woman in love, translated into sound. There are also 116 images showing life on Earth, our planet, our civilization, our attempts to explain who we are and where we come from. The golden record was included as a message to any extraterrestrial intelligence that might someday encounter Voyager 1. The odds of that happening are astronomically small, of course. Space is so vast and empty that Voyager 1 could travel for billions of years without coming close to another star system. And even if it did, the chances of an intelligent civilization being there and being technologically advanced enough to retrieve Voyager 1 and decode the record are vanishingly tiny. But that's not really the point. The golden record is as much a message to ourselves as it is to hypothetical aliens. It's a snapshot of humanity at a particular moment in time, a declaration that we exist, that we're curious, that we want to reach out and connect with whatever else might be out there. It's an act of hope and optimism, a belief that the universe is not just a cold and uncaring void, but a place where meaning and connection are possible. And in a way, that brings us back to the question of what lies beyond the edge of the universe. Because ultimately, that question isn't just about physics or cosmology, it's about meaning. It's about our place in the grand scheme of things. It's about whether the universe has a purpose or whether we're just an accident, a brief flicker of consciousness in an otherwise indifferent cosmos. Science can't answer those questions, at least not directly. Science can tell us how the universe works, what it's made of, how it began, and how it might end. But science can't tell us why the universe exists or what it all means, or whether there's something beyond the physical laws we can measure and observe. Those are questions for philosophy, for religion, for each individual to grapple with in their own way. But science can give us context. It can show us the scale of what we're dealing with. It can reveal the beauty and complexity of the cosmos. And it can inspire us to keep asking questions, to keep exploring, to keep pushing the boundaries of what we know and what we can imagine. Voyager 1 embodies that spirit of exploration. It's a machine, yes, built of metal and electronics, following the laws of physics as it moves through space. But it's also an extension of human consciousness, a physical manifestation of our desire to understand the universe. Every signal it sends back, every measurement it takes, is another piece of the puzzle, another step toward understanding the cosmos we inhabit. Let's think for a moment about the sheer improbability of Voyager 1's existence. Think about all the things that had to happen for us to build and launch this spacecraft. First, the universe itself had to come into being with physical laws that allow for the existence of matter and energy. Stars had to form and die, creating the heavy elements necessary for planets and life. A planet like Earth had to form in just the right location, with just the right conditions for life to emerge and evolve. Life had to develop from simple chemicals into complex organisms. Evolution had to produce intelligence, consciousness, the ability to ask questions and seek answers. Human civilization had to arise. With language and culture and technology, we had to discover the laws of physics, develop mathematics, build machines that could carry us beyond our planet, and we had to choose to do so to invest resources and effort into exploring space, even though the benefits were uncertain and the challenges were enormous. All of that had to happen in that specific sequence for Voyager 1 to exist. The odds against it are staggering, almost beyond calculation. And yet, here we are. Voyager 1 is out there right now, moving through interstellar space, a testament to the unlikely but undeniable fact that the universe has produced conscious beings who can wonder about it and explore it. Now, some people look at those odds and conclude that there must be a purpose behind it all, some guiding intelligence or cosmic plan that made it inevitable. Others look at the same odds and conclude the opposite, that we're just incredibly lucky, that our existence is a fluke, a random occurrence in a universe that's mostly empty and indifferent. Science doesn't favor either interpretation. The data is what it is. How we interpret it, what meaning we assign to it, that's up to us. But here's what we can say for certain. The universe is vast beyond comprehension, ancient beyond imagination, and filled with wonders we're only beginning to understand. Voyager 1 has shown us a tiny fraction of that vastness, a glimpse of the space between the stars, a reminder that there's so much more out there than we can ever hope to explore directly. And yet, we continue to try. We build telescopes like the James Webb Space Telescope, peering deeper into space and further back in time than ever before. We send probes to distant planets and moons looking for signs of life, searching for answers to fundamental questions about our origins and our place in the cosmos. We develop new theories, new mathematical frameworks, new ways of understanding the universe at scales both large and small. Each discovery raises new questions. Each answer leads to deeper mysteries. The more we learn, the more we realize how much we don't know. It's a humbling process, but also an exhilarating one, because every new discovery, every new piece of data brings us a little closer to understanding the truth about the universe we inhabit. Let's consider some of the biggest mysteries that remain, questions that Voyager 1 and other missions might help us answer, even if only indirectly. One of the most profound is the nature of dark matter and dark energy. According to our best measurements, the matter we can see, the stuff that makes up stars and planets and galaxies, accounts for only about 5% of the total mass energy content of the universe. The rest is invisible, detectable only through its gravitational effects. About 27% of the universe is dark matter, some kind of particle or field that doesn't interact with light but does exert gravitational force. We know it's there because galaxies rotate faster than they should based on the visible matter alone, and because light from distant objects is bent by gravitational lensing in ways that require more mass than we can see. But we don't know what dark matter is made of. It could be exotic particles that we haven't yet detected, or it could be something even stranger, like primordial black holes or modifications to the laws of gravity itself. The remaining 68% of the universe is dark energy, an even more mysterious force that seems to be pushing space apart, causing the expansion of the universe to accelerate. We know dark energy exists because we can measure the rate of expansion using distant supernovae as cosmic measuring sticks. And the data clearly shows that expansion is speeding up, not slowing down as we would expect from gravity alone. But we have no idea what dark energy actually is. It might be a property of space itself, a kind of energy inherent in the vacuum. Or it might be something else entirely, something beyond our current understanding of physics. These mysteries are connected to the question of what lies beyond the edge of the universe. If we don't understand what most of the universe is made of, how can we claim to understand its ultimate nature or structure? Dark matter and dark energy might hold clues to the deeper workings of the cosmos, to the laws that govern reality at the most fundamental level. And those laws, in turn, might tell us something about what lies beyond our observable horizon, whether the universe is finite or infinite, whether it's part of a larger multiverse, or something even more strange. Voyager 1 can't directly study dark matter or dark energy. Its instruments weren't designed for that, And in any case, these phenomena operate on scales far larger than anything a single spacecraft can measure. But Voyager 1 is part of the broader scientific endeavor to understand the universe. The data it collects about the interstellar medium, about cosmic rays and magnetic fields, contributes to our overall picture of how the galaxy works. And that picture, in turn, helps us refine our theories about the universe as a whole. There is also the question of whether we're alone in the universe. This is perhaps the most emotionally resonant of all cosmic mysteries. Are we the only intelligent beings in the cosmos? Or is there life elsewhere, perhaps even civilizations far more advanced than our own? The universe is so vast, with so many stars and planets, that it seems almost impossible that we're alone. And yet, we haven't found any evidence of other intelligent life. No radio signals, no unexplained phenomena, no visitors from distant stars. This is sometimes called the Fermi paradox, named after the physicist Enrico Fermi, who supposedly asked, "Where is everybody? If the universe is teeming with life, why haven't we seen any sign of it?" There are many possible answers. Maybe life is common, but intelligence is rare. Maybe intelligent civilizations tend to destroy themselves before they can spread across the stars. Maybe they're out there but communicating in ways we can't detect. Or maybe they've simply chosen not to contact us. Or maybe we really are alone, the only conscious observers in an otherwise lifeless cosmos. Voyager 1 carries that golden record, that message to potential extraterrestrial civilizations, but it's unlikely to ever be found by anyone other than us. The spacecraft is just too small, space is too big, and the odds are too long. But the gesture matters. It represents our hope that we're not alone, our desire to reach out and make contact with whatever else might be out there. And in recent years, that hope has been bolstered by new discoveries. We've found thousands of exoplanets, planets orbiting other stars, many of them in the habitable zone where liquid water could exist on their surfaces. We've detected organic molecules in interstellar space, the building blocks of life floating in the void between the stars. We've found evidence of subsurface oceans on moons in our own solar system, like Europa and Enceladus, places where life might exist even now, hidden beneath layers of ice. These discoveries don't prove that life exists elsewhere, but they show that the ingredients for life are common throughout the universe. The same chemistry that gave rise to life on Earth is present in many other places. If life could arise here, it seems reasonable to think it could arise elsewhere as well. And if life is common, then perhaps intelligence is too, or at least not impossibly rare. But even if we never find evidence of other intelligent beings, even if we're truly alone in the cosmos, that doesn't diminish the significance of our existence. In some ways, it makes it more profound. If we're the only conscious observers, then we're the only way the universe can know itself, the only means by which the cosmos can reflect on its own existence. We become, in a sense, the universe's way of understanding itself. Carl Sagan expressed this idea beautifully when he said, "We are a way for the cosmos to know itself." That phrase has become famous, repeated countless times, but it's worth sitting with it for a moment, really considering what it means. The atoms in your body, the carbon and oxygen and nitrogen, were forged in the cores of ancient stars. Those stars lived and died billions of years ago, and when they died, they scattered their material into space. That material eventually coalesced into new stars, new planets, and eventually into you. You are literally made of stardust, and so is Voyager 1. The metal hull, the electronic components, the scientific instruments, All of it came from the same cosmic furnace, the same process of stellar alchemy that created every element heavier than hydrogen and helium. In a very real sense, we and Voyager 1 are siblings, born from the same cosmic ancestry, products of the same 13.8 billion year journey from the Big Bang to the present moment. And now Voyager 1 is traveling through the space between the stars, through the very medium from which it was born. It's returning to the cosmic ocean, carrying with it the knowledge and curiosity of the civilization that built it. There's something deeply moving about that, something that transcends the technical details of its mission. Voyager 1 is a symbol of who we are and what we aspire to be. Let's think about what the far future might hold for Voyager 1. Its power supply, a radioisotope thermoelectric generator, is slowly decaying. By the 2030s, maybe the early 2040s at the latest, it won't be able to power any of its instruments. The last signals will be sent, the final data transmitted, and then silence. Voyager 1 will continue its journey, but will no longer be able to hear from it. It will become a ghost ship, drifting through the void, still moving, but no longer communicating. But even then, its journey won't be over. Voyager 1 will keep moving, coasting through the galaxy on momentum alone, following the orbital path determined by its launch trajectory and the gravitational pulls it encountered along the way. In about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. It won't be close enough to be captured by the star's gravity, just a distant visitor passing through the neighborhood. And then it will continue on, through thousands, millions, perhaps even billions of years. The galaxy will rotate, stars will be born and die, and Voyager 1 will be there. A silent witness to cosmic changes beyond anything we can imagine. Its golden record will still be intact, protected from the radiation and dust of space by its aluminum cover. The images and sounds from Earth will remain, a time capsule from a civilization that may or may not still exist by then. Think about that for a moment. Long after humanity is gone, whether through extinction or evolution into something we wouldn't recognize, Voyager 1 will still be out there. It will outlive our entire species. It will outlive our sun. In about 5 billion years, when the sun expands into a red giant and engulfs the inner planets, including Earth, Voyager 1 will be safely far away, continuing its eternal journey through the galaxy. It will be the last remaining evidence that we ever existed, the final monument to human civilization. Unless, of course, someone finds it, some other intelligence, some other civilization that has also learned to explore the stars. They would encounter this strange artifact, study its design, decipher its message, and learn that once, long ago, on a small blue planet orbiting an average yellow star, there existed a species that wondered about the universe and reached out to touch it. They would learn that we existed, that we were here, that we mattered, at least to ourselves. It's an almost impossibly romantic notion, and the odds against it are staggering. But it's not impossible, and that slim possibility, that chance that Voyager 1 might one day speak for us to someone else, gives the mission a significance that transcends its scientific value. It makes Voyager 1 more than just a machine. It makes it a message in a bottle, cast into the cosmic ocean, carrying the hopes and dreams of an entire species. Now let's return to the central question that's been weaving through this entire exploration. What lies beyond the edge of the universe? We've discussed several theories, from the straightforward idea of infinite space to the mind-bending concepts of multiverses and simulations. But there's another possibility we haven't fully explored yet, one that challenges our most basic assumptions about the nature of reality itself. This possibility suggests that the question itself might be flawed, that asking what lies beyond the edge of the universe is like asking what's north of the North Pole. It's a category error, a question that assumes something that isn't true. Let me explain what I mean. When we think about space, we naturally think of it as a container, a stage on which the cosmic drama unfolds. We imagine the universe as existing within space, and so we assume there must be something outside the universe, some larger space in which it's embedded. But according to general relativity, Einstein's theory of gravity and space-time, space itself is part of the universe. It's not a container that holds the universe. It's a component of the universe, as fundamental as matter and energy. If space is part of the universe, then asking what lies beyond the edge of the universe is asking what lies beyond space itself. And that may not be a meaningful question. It's like asking what happened before time began. Before the Big Bang, there was no time. So the concept of before doesn't apply. The question assumes the existence of something, in this case time, that didn't exist yet. Similarly, asking what lies beyond space assumes that there's something for space to be beyond, some larger framework in which space exists. But if space is fundamental, if it's not embedded in anything else, then there is no beyond. This is a difficult concept to grasp because our brains evolved to navigate three-dimensional space. We are hardwired to think of space as absolute, as a fixed background against which objects move. But general relativity tells us that space is dynamic, flexible, capable of bending and stretching in response to the presence of matter and energy. Space-time is woven together with the fabric of reality itself. It's not separate from the universe. It is the universe, or at least a crucial part of it. So perhaps the edge of the universe, if it exists, isn't a boundary in space. Perhaps it's a boundary of space itself, a limit beyond which space simply doesn't exist. And if space doesn't exist, then neither does time, because they're linked together in the four-dimensional structure of space-time. Beyond the edge, there would be no when and no where, no possibility of existence as we understand it. There would be nothing, not even the nothing of empty space, just absolute, incomprehensible non-existence. That's a disturbing thought, in some ways more disturbing than the idea of infinite space. At least with infinity, we can imagine more of what we already know, an endless repetition of galaxies and stars. But true non-existence, the absolute absence of space and time, that's something our minds can't really picture. We can say the words, but we can't form a mental image of it. It's beyond the reach of human intuition. And yet, this might be the answer. The edge of the universe might be the edge of existence itself, the boundary beyond which nothing can be said to exist because the very concepts of existence and location break down. It's not that there's something beyond we can't see or reach. It's that there is no beyond. The universe is all there is in the most literal and absolute sense possible. But even if that's true, even if the universe is all that exists, it still leaves us with questions. Why does the universe exist at all? Why these physical laws and not others? Why is there something rather than nothing? These are questions that science may never be able to answer, not because we lack the tools or the intelligence, but because they may lie outside the domain of science entirely. They're questions about the ultimate nature of reality, about why reality exists in the first place, and those questions may require philosophical or even theological answers, not scientific ones. Voyager 1 can't help us answer those questions. No spacecraft can, no matter how far it travels or how sophisticated its instruments. But Voyager 1 does remind us that the questions are worth asking. It reminds us that we're curious beings, that we want to understand not just how things work, but why they are the way they are. That curiosity is one of our defining characteristics as a species. It's what drove us to build Voyager 1 in the first place. Let's think about some of the other cosmic mysteries that relate to the edge of the universe and what might lie beyond. One of the most intriguing is the question of cosmic inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang. The evidence for inflation is strong. It explains why the universe is so uniform on large scales, why it appears flat, why we don't see certain exotic particles that should have been created in the Big Bang. But we don't fully understand what caused inflation or how it worked. Some versions of inflation theory suggest that it never really ended. Instead, it created countless bubble universes, each one a separate space-time, each one potentially with different physical laws. Our universe is one such bubble, and the edge we observe is simply the edge of our bubble. Beyond it, there might be other bubbles, other universes, forever inaccessible to us because they're separated by regions of space that are still inflating. In this scenario, the multiverse isn't just a theoretical possibility. It's a natural consequence of the physics that created our universe. And if that's true, then the question of what lies beyond our universe has a clear answer, at least in principle. More universe lies beyond, just not our universe. Other spacetimes, other realms of existence, each one as real and substantial as our own, but forever beyond our reach. The implications of this are staggering. It would mean that our universe, vast as it is just a tiny part of a much larger structure, a cosmic landscape of universes, each one a separate experiment in the possibilities of physics. Some of those universes might be similar to ours, with stars and galaxies and perhaps even life. Others might be radically different, with physics so alien that nothing recognizable could exist there. And there would be no way to ever visit them, no way to confirm their existence except through the indirect evidence provided by inflation theory. This is one of the most controversial ideas in modern cosmology. Many physicists love it because it seems to follow naturally from our best theories of the early universe. Others hate it because it's unfalsifiable, at least with current technology. If we can never observe these other universes, never gather direct evidence for their existence, then is it really science? Or is it metaphysics, speculation dressed up in mathematical equations? It's a fair question, and there's no easy answer. Science has always relied on observation and experiment to test theories. But what do we do when our theories predict things that are, by their very nature, unobservable? Do we abandon those theories, even if they successfully explain everything we can observe? Or do we accept them with the caveat that we can never be completely certain they're correct? It's a dilemma that highlights the limitations of the scientific method when applied to questions of ultimate cosmic scale. Voyager 1, in its own small way, helps us grapple with these questions by exploring the space beyond our solar system, by measuring the interstellar medium, by demonstrating that it's possible to send human artifacts into the larger galaxy. It expands our perspective. It reminds us that the universe is bigger than we can easily comprehend, and that there are always new frontiers to explore, new questions to ask, new mysteries to unravel. Consider the cosmic microwave background, the faint glow of radiation left over from the Big Bang. It fills all of space, a constant reminder of the universe's fiery beginning. Scientists have mapped this radiation in exquisite detail, looking for tiny variations in temperature that reveal how matter was distributed in the early universe. These variations are the seeds from which galaxies grew, the initial density fluctuations that gravity amplified over billions of years into the cosmic web of structure we see today. But there's something odd about the cosmic microwave background. There are patterns in it, alignments and features that seem too pronounced to be random. Some scientists have suggested that these patterns might be evidence of something beyond our observable universe. Perhaps the gravitational influence of other universes in a larger multiverse, or perhaps the signature of the overall geometry of space on scales larger than we can directly observe. These ideas are speculative, and most physicists are skeptical. The patterns might just be statistical flukes, or they might be artifacts of how we analyze the data. But they're tantalizing hints that there might be more to discover, more secrets hidden in the structure of the universe itself. And that's what makes cosmology so exciting. Every answer leads to new questions. Every discovery opens new avenues of inquiry. Voyager 1's journey, while focused on a much smaller scale, embodies the same spirit of exploration. It's pushing the boundaries of what we know, venturing into regions no human-made object has reached before, sending back data that helps us understand the cosmos better. And even though it will never reach the edge of the universe, even though its journey is infinitesimal compared to cosmic distances, it still matters. It still contributes to the larger project of understanding where we are and what surrounds us. Let's take a moment to consider the practical implications of these cosmic mysteries. Why does it matter what lies beyond the edge of the universe? Why should we care about multiverses or cosmic inflation or the ultimate fate of space-time? These questions seem so abstract, so removed from everyday life. What difference does it make to know the answers? In one sense, it doesn't make any practical difference at all. Knowing what lies beyond the observable universe won't help us cure diseases or solve climate change or improve anyone's daily life. But in another sense, it makes all the difference in the world. Because these questions are about our place in the cosmos, about the nature of reality, about whether existence has meaning or purpose. And those questions, abstract as they are, shape how we see ourselves and how we live our lives. Throughout human history, our understanding of the universe has profoundly influenced our philosophy, our culture, our values. When people believed the Earth was the center of the universe, it reinforced a view that humans were special, that we were the purpose of creation. When Copernicus showed that Earth orbits the Sun, not the other way around, it challenged that view and forced us to reconsider our place in the cosmos. When Hubble discovered that our galaxy was just one among billions, it further diminished our cosmic significance. And yet, paradoxically, each of these discoveries also elevated us. Because while they showed that we're not at the center of the universe, they also showed that we're capable of figuring that out. We're capable of understanding the cosmos, of building instruments that can detect galaxies billions of light years away, of formulating theories that explain the origin and evolution of the universe. That's remarkable. It suggests that consciousness, intelligence, the ability to ask questions and seek answers, These might be among the most significant phenomena in the cosmos. Voyager 1 is a product of that intelligence, that curiosity. It's a physical manifestation of our desire to explore and understand. And its journey, humble as it is in cosmic terms, represents something profound about what it means to be human. We're not content to simply exist. We want to know why we exist, what surrounds us, what lies beyond the horizon. That drive to explore, to push boundaries, to ask questions that might not have answers, that's as fundamental to human nature as anything else. So when we ask what lies beyond the edge of the universe, we're not just asking a scientific question. We're expressing something deeper, a yearning to understand our place in the grand scheme of things. And even if we never find a definitive answer, even if the question remains forever beyond our ability to resolve, the act of asking it matters. It defines us as conscious beings who care about truth, who want to make sense of existence, who refuse to accept ignorance when knowledge might be possible. Let's consider what future missions might teach us about these cosmic mysteries. Voyager 1 was launched in 1907 with technology that now seems laughably primitive, and yet it's still functioning, still contributing to our knowledge. What might we learn from missions that haven't been launched yet? Missions that will use technologies we're only beginning to develop. There are plans for new interstellar probes, spacecraft that would travel much faster than Voyager 1, using technologies like solar sails or nuclear propulsion. These probes might reach nearby star systems within a few decades rather than millennia. They could study exoplanets up close, search for signs of life, explore the structure of the interstellar medium in much greater detail. Each new mission would add to our understanding, filling in gaps in our knowledge, revealing new questions we hadn't thought to ask. There are also plans for more powerful telescopes, both on Earth and in space. The James Webb Space Telescope, launched in 2021, is already transforming our view of the early universe, detecting galaxies that formed just a few 100 million years after the Big Bang. Future telescopes might be even more powerful, capable of imaging exoplanets directly, searching for biosignatures in their atmospheres, perhaps even detecting artificial signals from other civilizations if any exist. And there are theoretical advances too, new ways of understanding the physics of the universe. Quantum gravity, the long-sought theory that would unify quantum mechanics with general relativity, might finally be within reach. If we can understand how gravity works at the quantum level, we might gain insight into the nature of space-time itself, into what happened in the first moments of the Big Bang, perhaps even into what lies beyond our observable universe. All of these developments, both technological and theoretical, will help us address the questions we've been exploring tonight. They won't give us easy answers, and they'll certainly raise new mysteries to replace the ones they solve. But they'll move us forward, inch by inch, toward a deeper understanding of the cosmos. And through it all, Voyager 1 will continue its journey, at least for a few more years. It will keep measuring the interstellar medium, keep sending back data, keep contributing to our knowledge. And even after it falls silent, even after we lose contact with it forever, it will remain a symbol of human exploration, a reminder that we reached out to touch the stars and succeeded, if only in a small way. Think about the engineers and scientists who built Voyager 1, who planned its mission, who have maintained contact with it for nearly 50 years. Many of them are retired now, or have passed away, but their work lives on, traveling through space, continuing the mission they started so long ago. It's a form of Immortality, a way of leaving a mark on the universe that will endure long after we're gone. Every person who contributed to Voyager 1, from the top scientists to the technicians who assembled it, they're all part of this ongoing journey. Their legacy is out there, moving through the void, exploring the cosmos on our behalf. There's something deeply moving about that. Something that speaks to our desire for meaning and significance. We're mortal beings living brief lives on a small planet, but through projects like Voyager 1, we transcend those limitations. We send part of ourselves out into the universe. We participate in something larger than ourselves. We contribute to a project that spans generations and will continue long after we're gone. And that brings us back, one more time, to the question of what lies beyond the edge of the universe. Because in a sense, that question is really about us. It's about our limitations and our ambitions. About what we can know and what will forever remain mysterious. About our place in a cosmos that's vastly larger and older than we are. The edge of the universe represents the boundary between the known and the unknown, between what we can observe and what lies forever beyond our reach. Voyager 1 is approaching a different kind of edge, the edge of our ability to communicate with it. Soon, within the next decade or two, it will cross that boundary and fall silent. We'll no longer know what it's experiencing, what it's measuring, what wonders it might be encountering. It will continue to exist, continue to travel, but from our perspective, it will have passed beyond our reach into a realm we can no longer access. In that sense, Voyager 1's journey mirrors our cosmic situation. We live in an observable universe, bounded by horizons we cannot cross. Beyond those horizons lies more universe, or perhaps something else entirely, but we cannot observe it directly. We can theorize, we can extrapolate from what we do see, but we cannot know for certain. Voyager 1 will face a similar limitation, traveling beyond our ability to track it, entering a region where it exists but cannot communicate with us. And yet, both Voyager 1 and we ourselves continue to push against those boundaries. We don't accept limits easily. We build bigger telescopes, send spacecraft further, develop new theories that might let us understand what lies beyond our direct observation. We refuse to be satisfied with ignorance when knowledge might be possible. That's a defining characteristic of consciousness, or at least of human consciousness. We want to know, we need to know. And we're willing to invest in enormous resources and effort into finding out. Let's think about the ultimate fate of the universe because it's connected to these questions about edges and boundaries. According to our current understanding, the universe will continue expanding forever, or at least for an almost unimaginably long time. As it expands, galaxies will move further apart, eventually passing beyond each other's cosmic horizons. The universe will become increasingly dark and empty as stars burn out and are not replaced. In trillions of years, all the gas needed to form new stars will be exhausted. The universe will be populated by dead remnants, white dwarfs and neutron stars and black holes, slowly fading into darkness. In even longer timescales, matter itself might decay, with protons breaking apart into lighter particles. Eventually, even black holes will evaporate through a quantum process called Hawking radiation. The universe will approach a state of maximum entropy, a heat death where no structure remains, no gradients of temperature or density, just a cold, dark, nearly uniform sea of particles and radiation. This is called the heat death of the universe, and it's the most likely fate based on our current understanding of physics. It's a depressing thought in some ways, the idea that everything we've built, everything we've created, everything that exists, will eventually fade into cold nothingness. The universe will forget that we ever existed, that galaxies ever shone, that life ever emerged from lifeless chemistry. All of it will be erased, dissolved into the growing darkness of cosmic entropy. But that fate is so far in the future that it's almost meaningless. We're talking about timescales of 10 to the 100 years or more. Numbers so large they're just abstract symbols, completely beyond human comprehension. For all practical purposes, for any timescale that matters to us or to any civilization that might arise in the future, the universe will remain a dynamic, interesting place, full of structure and complexity and the possibility of life. And who knows, our understanding of physics might be incomplete. There might be processes we haven't discovered yet that could prevent heat death or transform it into something else. The universe might be cyclic, collapsing and rebounding in an endless series of big bangs. Or it might be part of a larger multiverse where our universe's death is just one event among countless others, no more significant in the grand scheme than the death of a single star. We don't know. We can't know, not yet. And that uncertainty, that open question about the ultimate fate of everything, is part of what makes cosmology so fascinating. We're living in a universe that's still revealing its secrets, still surprising us, still challenging our assumptions about how reality works. Voyager 1 won't be around to see any of this, of course. It will be destroyed long before the heat death of the universe, probably within 1 billion years or so. It might collide with some object, or be torn apart by the gravitational field of a star it passes to, close to, or simply accumulate enough damage from cosmic rays and micrometeorites to fall apart. But for now, for these brief moments in cosmic time, it exists and it's exploring, and it's telling us about the universe we live in. Let's take a moment to appreciate how remarkable that is. Voyager 1 is a machine, yes, but it's a machine that's fulfilling a purpose, carrying out a mission, contributing to something larger than itself. In that sense, it has a kind of meaning, a kind of significance that transcends its physical nature. It's not conscious, it doesn't have feelings or desires, but it represents the consciousness and desires of the beings who created it. It's an extension of humanity reaching out into the cosmos on our behalf. And in creating Voyager 1, we've done something that might be unique in the universe, or at least very rare. We've sent a piece of our world out into the galaxy, carrying information about who we are and where we come from. We've made it possible for our existence to be known beyond our planet, beyond our solar system, potentially to beings we'll never meet and can barely imagine. That's an extraordinary achievement, a testament to human creativity and ambition. Now, as we near the end of our journey together tonight, let's return one final time to the central question. What lies beyond the edge of the universe? We've explored many possibilities. Infinite space, stretching forever in all directions. A finite but unbounded universe, curved back on itself like the surface of a sphere. A multiverse, with countless bubble universes each separated from the others by eternally inflating space. Or perhaps nothing at all, the edge of space-time itself, beyond which the concepts of existence and location have no meaning. Each of these possibilities has its own implications, its own philosophical consequences. An infinite universe suggests endless possibility, but also endless repetition, with infinite copies of everything that exists. A finite universe feels more comprehensible, but raises questions about what could possibly curve space back on itself. What lies beyond the curvature? A multiverse is intellectually satisfying in some ways, but troubling in others, suggesting that our universe is just one random possibility among infinite others. And a true edge to existence challenges our deepest intuitions about the nature of reality. We don't know which of these is correct. We may never know. But in asking the question, in thinking seriously about these possibilities, we're engaging in one of humanity's oldest and most important activities. We're trying to understand the world around us, to make sense of our existence, to find meaning in a universe that often seems indifferent to our presence. Voyager 1, in its own way, is part of that quest for understanding. It was built to explore, to gather data, to expand our knowledge of the cosmos, and it succeeded beyond anyone's expectations, revealing wonders and raising questions that will occupy scientists for generations to come. Its journey reminds us that exploration is worthwhile, that pushing boundaries matters, that the quest for knowledge is one of the things that makes us human. As Voyager 1 continues its eternal journey through the galaxy, moving further from home with every passing second, it carries with it a message about who we are. We're a species that looks up at the stars and wonders. We're beings who refuse to accept that some questions are too big to ask, some mysteries too deep to explore. We're conscious minds trying to understand an unconscious universe, and that attempt, doomed as it might ultimately be, is perhaps the most beautiful thing about existence. The edge of the universe, whatever it is, represents the boundary of our knowledge and our understanding. But it's not a permanent boundary. It's a frontier, a challenge, an invitation to keep exploring, keep questioning, keep pushing the limits of what we can know. And as long as we continue to do that, as long as we continue to send spacecraft like Voyager 1 into the unknown, as long as we continue to ask questions about what lies beyond the edge of everything, we're fulfilling our role as conscious observers of the cosmos. Maybe that's the real answer to our question. What lies beyond the edge of the universe? More questions, more mysteries, more opportunities for exploration and discovery. The universe, in all its vast, incomprehensible glory, invites us to explore it, to understand it, to wonder at it. And through missions like Voyager 1, through telescopes and theories and experiments, we accept that invitation. We reach out to touch the infinite, even knowing we can never fully grasp it. And in that reaching out, in that eternal quest for understanding, we find meaning. Not meaning imposed from outside, not meaning given to us by some cosmic authority, but meaning we create ourselves through our curiosity, our creativity, our refusal to be satisfied with ignorance. The universe may not care about us, may not even be aware of our existence, but we care about the universe. We want to understand it, to explore it, to find our place within it. And that caring, that desire, that's what makes us significant, at least to ourselves. Voyager 1 is still out there, still moving through the dark between the stars. It's traveled further than any human artifact in history, and it's not done yet. For a few more years, maybe a decade or two, it will continue to send back data, continue to teach us about the cosmos. And then, when its power finally fails, when the last signal is transmitted and the last instrument goes dark, it will continue anyway, drifting through the galaxy on momentum alone, a silent monument to human curiosity. And somewhere, billions of miles from Earth, that tiny spacecraft carries a golden record, a collection of sounds and images from a world Voyager 1 left behind nearly 50 years ago. On that record, encoded in analog grooves that could last for billions of years, are pieces of our world. Music and voices, natural sounds and scientific data, images of people and places and things that define what it means to be human. It's a message to whatever intelligence might someday find it, but it's also a message to ourselves, a reminder of who we were and what we valued when we sent Voyager 1 on its journey. The message says, essentially, we were here. We existed. We wondered about the universe, and we reached out to explore it. We didn't know what lay beyond the edge of our understanding, but we tried to find out anyway. We built this spacecraft, sent it into the unknown, hoped that it might discover something new, something wonderful, something that would help us understand our place in the cosmos. We were small and brief and fragile, living on a tiny planet orbiting an average star. But we looked up at the stars and we dreamed of reaching them. And in our own small way, we did. Let's take a moment to consider what Voyager 1 has taught us about the nature of exploration itself. When the mission was planned in the early 1970s, the scientists and engineers involved couldn't have predicted everything the spacecraft would discover. They designed it with specific goals in mind, studying Jupiter and Saturn, but they also built in flexibility, the ability to adapt and continue beyond those initial objectives. That foresight, that willingness to plan for the unexpected, has been one of the mission's greatest strengths. Think about how many times Voyager 1 has surprised us. The volcanic activity on Io was completely unexpected. The complexity of Saturn's rings went far beyond what anyone had imagined. The behavior of the heliosphere, the boundary between our solar system and interstellar space, turned out to be more complicated than theoretical models had predicted. Each of these discoveries required scientists to revise their understanding, to adjust their theories, to acknowledge that the universe is more intricate and surprising than we give it credit for. This pattern of surprise and revision is central to how science works. We build models based on what we know, we make predictions about what we'll find, and then we test those predictions through observation and experiment. When the data contradicts our expectations, we don't ignore it or dismiss it. We change our models. We adapt our understanding. We admit that we were wrong and we try again, incorporating the new information into a better, more accurate picture of reality. Voyager 1 has been a perfect tool for this process. It's gone places we couldn't go ourselves, made measurements we couldn't make from Earth, shown us things we wouldn't have discovered any other way. And in doing so, it's forced us to be humble, to recognize the limits of our knowledge, to accept that the universe doesn't always conform to our expectations. That's a valuable lesson, one that extends far beyond space exploration into every aspect of human inquiry. Now, let's think about what Voyager 1's journey tells us about the concept of home. For most of human history, home meant a specific place, a village or a city or a region of Earth. Our ancestors rarely traveled more than a few dozen miles from where they were born. The world was small, bounded by the horizon, limited to what could be reached on foot or horseback or by sailing ship. Home was concrete, tangible, something you could return to after a journey. But as our technology advanced, as we developed faster ways to travel and communicate, the concept of home expanded. First to encompass a nation, then a continent, then the entire planet. The famous photograph of Earth from the Moon, taken during the Apollo missions, showed us our planet as a unified whole. a single home for all of humanity. National boundaries disappeared from that perspective. Political divisions became invisible. We saw ourselves as one species, sharing one world, floating in the darkness of space. Voyager 1's journey takes this perspective even further. From its vantage point in interstellar space, Earth isn't just small, it's almost invisible, a pale blue dot lost in the vastness. And yet, it's still home. It's still the place where everything we know and love exists, the place where our species evolved, the place where human history unfolded. Voyager 1 is moving away from that home, perhaps never to return, and yet it remains connected to it, still sending signals back, still reporting on what it finds in the cosmic wilderness. There's a bitter sweetness to this, a sense of loss mixed with wonder. Voyager 1 is the ultimate explorer, venturing into unknown territory, never looking back. But it's also eternally tethered to the world that created it, defined by its origins even as it moves beyond them. In that sense, Voyager 1 mirrors the human condition. We're explorers by nature, always pushing boundaries, always seeking new horizons. But we're also creatures of place, shaped by where we come from, carrying our homes with us even as we venture far from them. Let's consider the role of time in Voyager 1's mission and in our understanding of the universe. Time is something we take for granted in our daily lives. It flows from past to future, marking the progression of events, giving structure to our experience. But in the context of the cosmos, time becomes strange and malleable. Einstein showed us that time is relative, that it passes differently for observers in different circumstances, that it's woven together with space in a four-dimensional fabric we call space-time. For Voyager 1, time passes slightly differently than it does on Earth. The spacecraft is moving at high speed, and according to relativity, time moves more slowly for objects in motion relative to stationary observers. The effect is tiny, just a few microseconds over the entire mission, but it's real and measurable. Voyager 1 is aging more slowly than the scientists who built it, experiencing time at a fractionally different rate than the rest of us. This might seem like a trivial detail, but it points to something profound about the nature of reality. Time isn't absolute. It's not a universal clock ticking away at the same rate everywhere. It's a property of the universe that can stretch and compress depending on motion and gravity. Near a black hole, time slows down dramatically compared to far away. At the event horizon, the boundary beyond which nothing can escape, time appears to stop entirely from the perspective of an outside observer. These time effects become important when we think about the edge of the universe. Remember, the observable universe is defined by how far light can travel in the time since the Big Bang, but that time, 13.8 billion years, is measured from our perspective. For photons, particles of light traveling at the speed of light, no time passes at all. From a photon's perspective, if it could have a perspective, its entire journey from emission to absorption happens instantaneously, with no duration whatsoever. The vast cosmic distances we measure, the billions of light years between galaxies, are experiences that only make sense for observers moving slower than light. Think about that for a moment. The universe looks different depending on how fast you're moving, how strong the gravitational field around you is, where you're located in space and time. There's no single objective view of reality, no universal perspective from which all observers would see the same thing. The cosmos is fundamentally observer-dependent, shaped by the circumstances of whoever or whatever is doing the observing. This doesn't mean reality is subjective or that anything goes. The laws of physics are the same everywhere. But the specific details of what you observe, how events unfold from your perspective, those can vary dramatically. Voyager 1 has its own unique perspective on the cosmos, different from ours. It's experiencing the universe from a location and velocity that no human has ever occupied. The stars look slightly different from where Voyager 1 is, shifted by parallax, the apparent motion of nearby objects against more distant backgrounds. The sun is dimmer, just another star among many. The cosmic microwave background, that faint glow from the Big Bang, has a slightly different temperature in different directions due to Voyager 1's motion through space. These are small differences, but they remind us that perspective matters, that where you are and how you're moving shape what you can see and know. Now let's explore another mystery related to the edge of the universe, one that's both scientifically fascinating and philosophically troubling. It's the question of whether the laws of physics are the same everywhere, or whether they might vary in different regions of space, perhaps even beyond our observable horizon. We've always assumed that the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and in all locations. The laws we discover here on Earth should apply equally well in distant galaxies, or so we believe. But what if that's not true? What if the physical constants we measure, things like the strength of gravity, or the charge of an electron, or the speed of light, are actually different in other parts of the universe? This idea sounds radical, but some versions of string theory and multiverse cosmology suggest it might be possible. In these theories, the physical constants aren't truly constant. They're parameters that can take different values in different regions of space, determined by random processes in the early universe, or by the specific way extra dimensions are configured. If this is true, then the edge of our observable universe might also be a boundary between regions with different physics. Beyond our horizon, the laws of nature might be subtly or dramatically different. Stars might not form the same way. Chemistry might work differently. Life as we know it might be impossible, while other forms of structure and complexity we can't imagine might flourish. It's a strange thought, one that challenges our deepest assumptions about the uniformity of nature. Voyager 1 can't directly test these ideas. It's not going to reach regions where physics is different, but it does provide data about the local environment, about how matter and energy behave in the interstellar medium, and that data helps us understand whether our theories are consistent. If we found anomalies, unexpected behaviors that couldn't be explained by known physics, it might hint that something deeper is going on, that our understanding is incomplete. So far, everything Voyager 1 has measured is consistent with standard physics. The universe, at least in our neighborhood, behaves as we expect. Let's think about the concept of infinity again, because it keeps coming up in discussions about the edge of the universe. Infinity is a mathematical concept that's easy to write down, but nearly impossible to truly comprehend. We can say that a line extends infinitely in both directions, or that there are infinitely many numbers between 0 and 1, but we can't really picture infinity. Our brains aren't built for it. We think in terms of finite quantities, bounded sets, things we can count or measure. And yet, infinity might be a real property of the physical universe. If space extends forever, if there is no edge, then the universe is literally infinite. Not just very large, not just bigger than we can measure, but actually truly infinite. And that has consequences that are hard to wrap your mind around. An infinite universe contains infinite matter, infinite energy, infinite possibilities. Every event that can happen will happen, not just once, but infinitely many times. Every configuration of particles that's possible will occur somewhere, including configurations identical to what we see around us. This leads to some deeply strange conclusions. In an infinite universe, there would be infinitely many planets exactly like Earth, with histories exactly like ours, populated by people exactly like us. There would be infinitely many versions of you reading these exact words, thinking these exact thoughts. Some of those versions would make different choices a moment from now, leading their lives down slightly different paths, but others would be perfectly identical, forever and always, exact duplicates in every possible way. Physicists call these duplicates Hubble volumes, regions of space so far away that light from them can never reach us, but which contain the same patterns of matter and energy as our own region. The distance to the nearest exact duplicate of our observable universe, if such duplicates exist, has been calculated. It's roughly 10 to the power of 10 to the power of 115 meters away. That's not a typo. It's 10 to the power of 115 meters, and then you raise 10 to that power. It's a number so large, it's meaningless. Vastly larger than the observable universe. Vastly larger than anything we can relate to human experience. And yet, if the universe is infinite, such duplicates must exist. The mathematics is clear. In an infinite space with finite possibilities for how matter can be arranged, every possible arrangement will occur, and will occur infinitely many times. It's a conclusion that follows logically from the premises, but it feels absurd, almost nonsensical. How can there be infinitely many copies of everything? How can the universe contain all of that without collapsing into meaninglessness? Maybe it doesn't matter. Maybe the existence of distant duplicates, forever unreachable and unobservable, doesn't affect us in any practical way. They're like the trees falling in forests with no one around to hear them. Philosophical curiosities that don't change how we live our lives or understand our immediate surroundings. Or maybe it does matter, because it changes how we think about uniqueness and identity and meaning. If you're not unique, if there are infinite copies of you scattered throughout an infinite cosmos, does your life have the same significance? Does it matter what choices you make if infinite other versions of you are making different choices? These are questions that keep philosophers awake at night. Science can describe the possibilities, can show us what might be true if certain assumptions hold. But science can't tell us how to feel about those truths, what moral or existential conclusions to draw from them. That's something each of us has to figure out for ourselves. Voyager 1, in its simplicity, offers a kind of answer. It doesn't worry about whether it's unique or whether there are infinite copies of it in other Hubble volumes. It simply does what it was designed to do. It explores, it measures, it reports back, it fulfills its purpose without needing to understand the cosmic implications of its existence. There's something admirable about that, a kind of purity of mission that we might do well to emulate. Let's turn our attention to another cosmic mystery, one that relates directly to what might lie beyond the edge of the universe. This is the mystery of the cosmological constant, a term Einstein introduced into his equations of general relativity to keep the universe static, neither expanding nor contracting. He later called it his greatest blunder when Hubble discovered that the universe is actually expanding. But in recent decades, the cosmological constant has made a comeback, though in a different form. We now know that the expansion of the universe is accelerating, driven by something we call dark energy. The cosmological constant is one way to explain dark energy, suggesting that space itself has an inherent energy density, a kind of pressure that pushes everything apart. This energy doesn't dilute as the universe expands. Instead, as more space is created, more dark energy appears, causing the expansion to accelerate faster and faster over time. Here's where it gets interesting. Quantum field theory, our best understanding of how particles and fields work at the smallest scales, predicts that empty space should have an energy density. The quantum vacuum isn't truly empty. It's filled with virtual particles constantly popping in and out of existence, a seething foam of quantum activity. When you calculate what the energy density of this quantum vacuum should be, you get a number. And that number is wrong, spectacularly, embarrassingly wrong. The predicted vacuum energy is about 10 to the power of 120 times larger than the observed dark energy density. That's not off by a little bit. That's off by 120 orders of magnitude, one of the largest discrepancies between theory and observation in all of physics. If the vacuum energy were really as large as quantum field theory predicts, the universe would be expanding so fast that atoms couldn't hold together, let alone stars and galaxies and planets. Nothing we observe could exist. So why is the vacuum energy so much smaller than it should be? Why is the cosmological constant, the amount of dark energy in the universe, exactly the tiny but non-zero value needed for the universe to exist in a form that allows for structure and complexity in life? This is one of the deepest unsolved problems in physics, and it might be connected to what lies beyond our observable universe. One possible answer involves the multiverse. If there are many universes, each with different values for the cosmological constant, then we naturally find ourselves in one where the value is right for our existence. Universes with too much dark energy would expand so fast that galaxies never formed. Universes with negative dark energy would collapse back on themselves too quickly for stars to ignite. We can only exist in a universe where the cosmological constant falls within a narrow range, so it's no surprise that we observe that range. This is called the anthropic principle, the idea that the universe appears fine-tuned for life, not because it was designed that way, but because we can only observe universes that are capable of producing observers. It's a controversial idea. Many physicists dislike it because it seems like giving up on finding a deeper explanation. But others embrace it, arguing that if the multiverse is real, the anthropic principle is the only logical way to explain why our universe has the properties it does. And if that's true, then what lies beyond the edge of our universe might be other universes with different cosmological constants, different physical laws, different possibilities for what can exist. We're in this universe not because it's special or unique, but because it's one of the few where creatures like us could evolve to ask these questions. Think about how strange that is. The edge of the universe might separate not just different regions of space, but different realms of possibility, different versions of physics, different answers to the question of how reality works. And we happen to live in the version that allows for stars and planets and life, not because anyone chose it or designed it that way, but simply because those are the only universes that can have inhabitants to wonder about them. Voyager 1 operates in our universe, with our physics, our cosmological constant, our particular set of laws and parameters. It's a product of this specific reality, built according to principles that only work here, in this cosmic neighborhood, in this version of the universe. If it could somehow cross into a region with different physics, it would cease to function. Its electronics scrambled by unfamiliar forces, its trajectory warped by altered gravitational laws. But it can't cross those boundaries, assuming they even exist. It's trapped, as we all are, in the universe that gave rise to us, exploring the only version of reality we can ever directly experience. Let's consider one more aspect of Voyager 1's journey before we approach our conclusion. This is the question of what it means to explore. Throughout history, exploration has been driven by many motives. Curiosity, certainly, but also the desire for resources, for territory, for knowledge that could provide strategic or economic advantages. The great explorers of the past, people like Columbus and Magellan and Cook, were seeking trade routes, new lands, opportunities for expansion and exploitation. Voyager 1's mission is different. It's not looking for resources we can extract or territories we can colonize. The distances involved make that impossible. Even if Voyager 1 discovered a planet made of pure gold or diamonds, we couldn't go there and bring it back. The spacecraft is traveling at 38,000 miles per hour, and it would still take tens of thousands of years to reach even the nearest star. Voyager 1 is engaged in pure exploration, seeking knowledge for its own sake, with no expectation of practical benefit or material return. That's actually quite rare in human history. Most exploration has been motivated by practical concerns, by the need or desire for something tangible. But Voyager 1 represents a different kind of impulse, a purely intellectual curiosity about the universe, a desire to know what's out there simply because it's out there. There's something noble about that, a kind of exploration that's untainted by conquest or exploitation, driven solely by the human need to understand. Of course, you could argue that there are practical benefits to space exploration, that the technologies developed for missions like Voyager 1 have applications in everyday life, that the knowledge we gain helps us understand our own planet better. And that's true. But those benefits are secondary, almost accidental. The primary goal is knowledge itself, understanding for its own sake. And that's a goal worth celebrating, worth investing in, worth pursuing even when the immediate payoff is unclear. Voyager 1 reminds us that we're capable of this kind of pure inquiry, this exploration driven by curiosity rather than need. It shows us at our best, reaching out to understand the universe not because we have to, but because we want to, because we're the kind of beings who care about truth and beauty and knowledge. That's a valuable reminder, especially in times when practical concerns and immediate problems dominate our attention. We need to remember that we're not just problem solvers and resource gatherers. We're also dreamers and explorers, capable of looking beyond our immediate circumstances to wonder about the larger cosmos we inhabit. As Voyager 1 moves through interstellar space, it carries that spirit of exploration with it. Every measurement it takes, every signal it sends back, contributes to our understanding of the universe. And even after it falls silent, even after we lose contact forever, it will continue to represent that spirit, a physical embodiment of human curiosity traveling through the cosmos long after we're gone. In that sense, Voyager 1 is more than just a machine. It's a symbol, a representation of our best qualities, our noblest aspirations, our deepest desire to understand the world around us. The edge of the universe, whatever it is, represents the ultimate frontier for that exploration. It's the boundary of what we can know, the limit of what we can observe and measure and understand. And yet, even that boundary isn't final. As our technology improves, as our theories become more sophisticated, as we gather more data and refine our models, that boundary shifts. What was unknowable yesterday becomes knowable today. What seems impossible now might be routine in 100 years. The edge keeps moving, always just beyond our reach, always inviting us to push a little further, to ask one more question, to seek one more answer. Voyager 1 has pushed that edge further than any human artifact before it. And whatever missions follow, whatever new technologies we develop, whatever discoveries await us in the future, they'll all be building on the foundation that Voyager 1 helped establish. Every spacecraft that ventures into the outer solar system, every measurement taken of the interstellar medium, every new theory about the structure of the galaxy or the universe beyond, they all benefit from what Voyager 1 has taught us. The mission continues, not just in the spacecraft itself, but in the ongoing project of human exploration and understanding that it represents. Think about what Voyager 1 means in the broader context of human history. For most of our existence as a species, we were bound to a single continent, then a single planet, then a single immediate cosmic neighborhood. Every generation expanded the map a little further. Ancient sailors ventured across seas that seemed endless. Explorers crossed continents that appeared to stretch forever. Astronomers turned their telescopes skyward and realized the stars were suns, that galaxies spiraled beyond our own, that the universe was vastly larger and stranger than anyone had imagined. Each discovery didn't diminish the mystery, it deepened it. Each answer spawned a dozen new questions. Voyager 1 is part of that continuum, but it represents something more. It's not just observing from afar. It's actually there, physically present in a realm no human will visit in our lifetimes. Perhaps not for centuries. It's our envoy, our representative, carrying not just instruments, but a message, a declaration that we exist, that we're curious, that we reached out across the cosmic darkness to say hello. The golden record attached to Voyager 1 contains sounds and images of Earth, greetings in dozens of languages, music from different cultures, the brain waves of a woman in love. It's a time capsule, a message in a bottle cast into an ocean so vast that the very concept of distance becomes almost meaningless. But even more than the record, Voyager 1 itself is the message. Its existence says that a species evolved on a small, rocky planet circling an ordinary star, and that species looked up, wondered, and then built something capable of leaving home forever. That journey, that audacious leap into the unknown, speaks to something fundamental about what it means to be human. We're explorers by nature, driven by curiosity that sometimes seems almost reckless in its intensity. We venture into places we're not designed for, places that could kill us, places where we don't belong by any reasonable measure, and we do it because we can't help ourselves. Because the questions are too compelling, the mysteries too tantalizing, the possibilities too magnificent to ignore. The data Voyager 1 sends back enriches our understanding in ways both profound and practical. Its measurements of cosmic rays help us understand the radiation environment future astronauts will face on long-duration missions. Its observations of the heliopause teach us about the protective bubble our sun creates and how it interacts with the rest of the galaxy. Its longevity demonstrates what's possible with thoughtful engineering and redundant systems, lessons that inform every spacecraft designed since. But beyond these tangible benefits, Voyager 1 serves another purpose. It reminds us that we're capable of thinking beyond our immediate concerns, beyond quarterly earnings and election cycles, beyond even our own lifespans. The engineers who designed Voyager 1 knew they wouldn't live to see it reach interstellar space. The scientists who planned its trajectory understood that the most interesting data might come decades after they retired or passed away. They built it anyway with care and precision and hope because they were contributing to something larger than themselves. That kind of long-term thinking, that willingness to plant trees whose shade you'll never sit in, that's rare in human affairs, but it's not absent. Voyager 1 proves it's possible. It demonstrates that we can commit to projects that span generations, that we can care about outcomes we'll never personally witness, that we can invest in knowledge for its own sake rather than immediate return. As Voyager 1 continues its journey, moving ever further from the sun, its transmissions growing weaker but still carrying precious data across billions of miles, it becomes more than a spacecraft. It becomes a symbol of human potential, of what we can achieve when we focus our ingenuity and resources on expanding the boundaries of knowledge. Every day it survives is a small miracle of engineering persistence. Every byte of data it transmits back represents a victory over entropy, distance, and the passage of time. And when Voyager 1 finally falls silent, when its plutonium power source decays beyond the point where it can run even a single instrument, when the last transmission fades into the cosmic background noise, the mission still won't be over. The spacecraft will continue on its trajectory, silent now, but still moving, still carrying the golden record, still representing humanity in the vastness between the stars. In about 40,000 years, it will pass within a few light years of a star called Gliese 445. Whether anything there will notice it, whether anything capable of understanding what it is and where it came from exists in that system, we have no way of knowing. But the possibility exists, the chance, however remote, that some other intelligence might one day find this artifact and decode its message. That possibility alone makes the journey meaningful. Voyager 1 teaches us that exploration isn't always about finding specific answers. Sometimes it's about asking better questions. Sometimes it's about building the tools and frameworks that future generations will use to make discoveries we can't even imagine yet. Sometimes it's simply about refusing to accept that any boundary is truly final, that any question is permanently unanswerable, that any frontier marks the end of human curiosity and ambition. The edge of the universe will always recede before us, but that doesn't make the pursuit futile. It makes it infinite. It means there will always be more to discover, more to understand, more to wonder about. Voyager 1 is still out there, still pushing forward, still expanding that edge 1 kilometer at a time. And we're here watching, learning, preparing for whatever comes next in this endless adventure of discovery. Now, as Voyager 1 continues its journey beyond our solar system, we're left with more questions than answers. But in the quiet vastness of space, perhaps the questions themselves hold their own beauty. The edge of the universe remains a mystery, and what lies beyond it may forever be unknowable. But in asking these questions, in building spacecraft to explore the cosmos, in refusing to accept the limits of our understanding, we participate in something profound. We become, for a brief moment in cosmic time, the universe's way of knowing itself. Where will we explore next? What new mysteries will we uncover? What answers will we find? And what new questions will those answers raise? The journey continues, whether through new missions, new telescopes, new theories, or simply through our continued wondering about the cosmos we inhabit. And maybe that's enough. Maybe the journey itself is the destination, the quest for understanding its own reward. If you enjoyed our cosmic journey, tonight, don't forget to subscribe and join us next time as we explore more of the universe's mysteries together. Until then, rest well and let your mind wander among the stars.